Climate change is the greatest engineering challenge of our time. While renewable energy and efficiency are vital, one powerful tool often overlooked is chemical engineering. Today, we're dividing into how chemical engineers can fight climate change through carbon capture and utilization. Every year, we pump out about 36 million tons of CO₂ into the atmosphere. The basic problem is that this gas traps heat and causes global warming. The challenge is simple to state but hard to solve. How do we stop releasing so much CO₂? And what do we do with the CO₂ that's already out there?
Our chemical industry still relies on fossil fuels for over 95% of its carbon sources. This dependence drives greenhouse gas emissions, economic risks, and resource insecurity. The transition away from oil and gas is not optional, it's already underway. The challenge? Developing alternative carbon sources and integrating renewable energy into production systems. Capturing carbon dioxide can be done through absorption with solvents, adsorption on solid materials, membranes, or cryogenic cooling. But capturing carbon dioxide is just the first step. Instead of simply storing it underground, what if we could use carbon dioxide as a resource? This is the idea of carbon capture and utilization. However, before utilization comes large-scale efficient capture. Improving capture technology means finding materials that can absorb carbon dioxide more selectively, operate at lower energy costs, and withstand harsh industrial conditions. Developing scalable systems that can be integrated into power plants, cement factories, and refineries is crucial. The goal is to make carbon dioxide capture not only effective but also economically viable, paving the way for industries to significantly reduce their carbon footprint and move closer to true climate neutrality. When it comes to utilization of carbon, there are various methods. First use can be to create synthetic fuels. By combining captured carbon dioxide with green hydrogen, we can create methanol and gasoline, produce olefins and aromatics, the building blocks of plastics, directly from carbon dioxide and hydrogen. Lock carbon into cement and carbonates, creating greener construction materials. All these were solutions to existing carbon in the environment. Now coming on to reducing the generation of further carbon.
The game changer is electrifying chemical production. Instead of heat from fossil fuels, engineers are designing processes powered by renewable electricity. Through electrocatalysis and photocatalysis, CO₂ can be converted directly into chemicals like ethylene glycol, acetic acid, or even ammonia, with a fraction of the carbon footprint of today's processes. This also allows distributed, small-scale plants better integrated into local economies. Across Europe, projects like Ocean, Terra, and Perform are exploring exactly like this, developing scalable reactors, new catalysts, and integrated systems for CO₂ conversion. These innovations are not only about reducing emissions but also about creating new value chains, such as producing bio-based polymers or fossil-free plastics. Beyond Europe, similar momentum is building across the globe. In Asia and North America, pilot plants are experimenting with direct air capture units coupled with renewable hydrogen systems, aiming to synthesize clean fuels like methanol and ammonia. In fact, engineers are learning to design modular setups that can fit into existing industrial clusters, making this transition smoother and more cost-effective. Universities and startups are joining hands with major industries to scale these solutions from lab to real-world factories. This collaboration between researchers, industries, and policymakers is exactly what can turn these early-stage innovations into global change. It's engineering being redefined, not just as a problem-solving, but as planet healing.
But it's not easy. Carbon capture and utilization still faces high costs, material challenges, and scalability issues. For example, designing durable catalysts, operating efficiency under fluctuating renewable power, and ensuring overall sustainability are major engineering hurdles. Still, progress is accelerating, and with every breakthrough, we move closer to a circular, low-carbon economy. The next challenge lies in integration. How to connect these technologies into existing power grids and industrial setups without major disruptions. Engineers are also exploring hybrid systems that combine biological and chemical pathways for carbon conversion, mimicking nature's efficiency while maintaining industrial speed. Governments are beginning to introduce incentives and carbon pricing mechanisms that make such projects financially viable, which in turn encourages more innovation. The race is no longer just about capturing carbon, it's about doing it smartly, affordably, and sustainably. Each step forward brings us closer to a world where industrial progress and climate responsibility go hand in hand.
Chemical engineering is more than just theory, it's climate action in motion. By rethinking carbon as a resource, not just waste, we can reinvent the chemical industry and fight climate change at its core. The future of carbon capture and utilization is not just about capturing CO₂, but about transforming it into the foundation of a sustainable economy. So, what do you think? Will we soon see everyday products made from captured CO₂? Let me know in the comments. And don't forget to like, share, and subscribe for more on science, technology, and the future of our planet. Because ultimately, it's not just about the science, it's about the story we tell through it. Every ton of CO₂ reused is a symbol of human creativity, resilience, and responsibility. If we can turn the world's biggest problem into an opportunity for innovation, we can redefine what progress truly means. And that's what engineering has always stood for, transforming challenges into chances for a better future.